Okay, thank you.
So we should start now.
Okay, should I just start? Or?
Okay. No, I will make a presentation. So we are extremely happy of having Bernd Sturmfels here. This is the first webinar of Orbita Mathematicae. This is the new journal of it's the official journal of the AMUMALCA, es la Unión Matemática de Latinoamérica y el Caribe, the Mathematical Union of Latin America and the Caribbean. And as we started this journal, we tried to get good papers and good papers. And guess who sent the first paper? First paper was sent by Bernd and co-authors, and it's the first paper published in Orbita Mathematicae last year in the first volume. So he's a very prolific and generous mathematician. And I think the best way of describing him is as a flow maker, opening research paths for a whole community of mathematicians working in applications of algebraic geometry. Now it's been rebranded as nonlinear algebra, but this is not just a rebranding. The idea is that it's a way of doing computations and applications, and also to develop the mathematics that's needed for that in a way that is friendlier for applied mathematicians just to have a better communication. So now this comes from a big project that is involved on application to particle physics. So I'm very happy to have you here. Please start with the lecture.
Yeah, thank you very much for the kind introduction. So indeed, our group is called Nonlinear Algebra at the MPI, Max Planck Institute, MIS, Mathematics and the Sciences. And so this is a new joint paper with Hadley, who's a physicist at the Institute for Advanced Study in Princeton, and Veronica, who is a PhD student in Leipzig. So the context is the Universe Plus project that I have with 3 physicists called Positive Geometry and Particle Physics and Cosmology. So in physics, a particle is often represented by its momentum vector, P, and this lives in Minkowski space. So that's a real vector space of dimension 1 plus d. D in our common world is equal to 3. So we have ambient 4-dimensional space with 3 space dimensions and 1 time dimension. But the inner product is not quite the usual one. We use the Lorentzian inner product, which has a signature plus, minus, minus, minus. So the dot product here between 2 vectors, momentum vectors P and Q, is the product that you see. P0, Q0 minus the sum of the products Pi, Qi. Now there's this thing called the universal speed limit that says you can never travel faster than the speed of light. And that requires that at all times, a particle has to satisfy the inequality that P dot P is greater or equal to 0. It has to stay in the light cone. And this is a non-trivial inequality because this is not the usual dot product, but the Lorentzian inner product. But the particle can be on the boundary, so it can satisfy that P dot P is equal to 0. And in this case, the particle is massless. So just for simplicity, photons are massless particles, but protons, electrons, and so on are massive particles, particles with masses. So we have this light cone that's defined by this inequality, P dot P greater or equal 0. And here's a picture for D equals 2. So it's the light cone for flatlanders. This is Veronica, who is the author. And of course, this cone has 2 convex parts. There's the past and there's the future. So this is the union of these 2 convex cones is the light cone. And this hand-built model is the D equals 2 case. And in the usual world we live in, D is 3. So this would be a 4-dimensional cone. Now we're going to be interested in the configurations of n particles that are in this cone. And we'll be especially interested in the massless case when all the particles are on the boundary. And towards the end, the case of most interest in physics is if we have the case of most interest in physics is if we have momentum conservation, meaning all these vectors sum to 0, but we'll get to this. So as I said, we now look at n particles, and each of them is represented by one of these momentum vectors. So P1 for the first particle, P2 for the second particle, and so on. Now, as in geometry and physics, the coordinates themselves are not so interesting. What's interesting are invariant quantities. So physical quantities are invariant quantities, invariant under the relevant symmetry group. And this is here the special orthogonal group SO1D. So those are invertible D+1 by D+1 matrices that fix the light cone, that fix the inner product. So this Lorentz group, and we're interested in quantities that are invariant under this action. Now, the ring of invariance is generated by the entries of this symmetric n by n matrix called Gram matrix. And in physics, they're called the Mandelstam invariants. So I simply take my momentum vectors here on the left side as a row vector. So I write this as an n by 1 plus d matrix. Then in the middle, I have my diagonal matrix for the Lorentzian inner product. And then the transpose on the right, a d+1 by n matrix. And then if I multiply this together, I get this symmetric matrix with entries Sij. So Sij is the inner product between the ith momentum vector and the jth momentum vector. And these inner products are invariant. So those are going to be the ones we're going to be interested in. Now, in the space of symmetric matrices, n by n matrices, the real symmetric matrices, we look at the Mandelstam region, which I'll denote by MNR, and that's the set of all matrices of this form for a fixed rank R. Now, this rank is at most 1 plus d, right? Because 1 plus d is the size of the middle matrix. So this n by n matrix has rank R, which is at most n plus d. And when I write M and R, I assume that the rank R is fixed. Now, as a variety, Zariski closure has known codimensions. So it has codimension binomial coefficient n minus R minus 1 choose 2 inside the ambient space, real vector space of symmetric n by n matrices. And what we're going to do is we're going to stratify this set, M and R, by the signs of Sij. So Sij can be positive, negative, or 0. And positive would mean that particles I and j are in the same cone. So they're either both in the future or both in the past. And if Sij is negative, then one of them is in the future and one of them is in the past. Here again, the light cone are 1 dimension lower. So this is for d equals 1. So here the light cone is this blue, the extreme rays in blue, and 3 particles. 1 particle is massless, P3, and then there are 2 other particles, P1 and P2, and the masses are just where the inner product is fixed. So M1 is the inner product of P1 with itself, and if this is positive, then I have this hyperboloid or hyperbola on which particles with a fixed mass can travel. Okay, so we're going to be interested in the Mandelstam region. I'm going to give you some descriptions of this. So as I said, this is a subset among the n by n real symmetric matrices of rank R. And to be in the Mandelstam region, meaning everybody obeys the speed limit, the Sij's have to be non-negative. So the SII, the diagonal entries, it's a typo, sorry, that should be SII. So diagonal entries should be non-negative, SII. That just means being in the light cone. And Lorentzian means that the matrix has precisely 1 positive eigenvalue and R minus 1 negative eigenvalue, R being the rank. Now, inside the Mandelstam region, there's a special region that's of most interest to currently in math called the Lorentzian region. This is simply those matrices where all the entries are non-negative. So let me write LNR for matrices that satisfy these two conditions, and in addition, the entries are non-negative. Well, this is a popular subject right now. So if I look at all such matrices where the rank R can be anything up to n, then these are the Lorentzian polynomials of degree 2. So Brandin and Peter and Juni He published a paper on Lorentzian polynomials, and this is a very active subject now at the interface of combinatorics and algebraic geometry. Is also parallel work in commutative algebra, so this in theoretical computer science. So this is a hot topic in math these days. Now, Peter Brandin, in a separate paper, proved that the Lorentzian region, as R, we take the union over all R, has nice topology. It's a topological ball, a full ambient dimension, n plus 1 choose 2. And now M, so in the Mandelstam region, we have a disjoint union. Take the interiors, we have a disjoint union of 2 to the n minus 1 such balls. And the stratification we are about to discuss, when restricted to the Lorentzian matrices, matches that in an upcoming popular paper. So there's a paper that's coming up by Baker, Herr, Kommer, and Lorscheid on Lorentzian polynomials and matroids. And what I'm about to say is consistent with their theory, except that we are allowing the matrices to have arbitrary signed entries. Okay, here is an equivalent formulation. So here I characterize the Mandelstam region by signs of the eigenvalues. Here is a characterization in terms of principal minors. And this is reminiscent of the characterization of positive definite matrices. So for the usual dot product, we have the notion of positive definite that says the principal minors are all positive. Here we have an alternating condition. So matrix S is in the Mandelstam region if and only if the principal minors have alternating signs. So what this says, the 1 by 1 principal minors are positive, the 2 by 2 are negative, and so on. Right? So 3 by 3. So for example, the 2 by 2 minors being negative, means that SII times SJJ is at most SIJ squared. Then the 3 by 3 minors are positive again, so we get an inequality among these 5 terms. Now thinking about this for a moment, combining these two inequalities, we conclude that on the Mandelstam region, we always have that Sij times Sik times Sjk is non-negative. That's an important inequality. Now, if you think about this for a moment, if this condition holds, then this implies that suppose you have a solution to these inequalities where all the Sij are non-zero, then this says that the sign of Sij is sigma I times sigma j for some fixed sign vector sigma. So there's some fixed sign vector sigma with pluses and minuses such that you multiply and you get the sign. That's equivalent to this condition. And in the application, sigma tells us who is in the past and who is in the future. Right? So if sigma I is negative, then the ith particle was in the past. And if it's positive, then it's in the future side of Veronica's cone. So from this discussion, we can already get a corollary. So summarize this. So the Mandelstam region is the union of 2 to the n minus 1 signed Mandelstam regions, one for each sign vector, right? So, well, of course, there are 2 to the n sign vectors, but a global sign flip makes no change, right? So there are 2 to the n minus 1 distinct ones. And if you take the corresponding union, then you get everything. and the relative interiors are pairwise disjoint. And as I said here, the sign vector distinguishes future from past. The one that the combinatorialists like, the Lorentzian region, is where the sign vector is all positive. So this means everything, either everything lies in the future or everything lies in the past. And we'll see in a moment, in the case of most interest in physics, this cannot happen, right? Because we're going to have momentum conservation, and then that reason will be empty. Okay, so what have I done? I've introduced the Mandelstam region. It's simply a subset in the space of symmetric matrices. It's reminiscent of positive definite matrices, except I have a sign adjustment for the Lorentzian inner product, and I have a stratification by sign vectors. So now I'm going to make my first physically meaningful assumption. So from now on, all particles are massless. So massless means like photons, for example, that the pi dot pi is 0. So in my matrix, this means the diagonal entries are all 0. Now, like Alicia said in the beginning, I've been working quite a bit on applications of algebraic geometry. And from that applied point of view, this is sort of a shocking new hypothesis, right? So usually in the last 20 years, when I thought about real symmetric matrices, they came from optimization, semi-definite programming. They came from statistics as covariance matrices, say of Gaussians. And those matrices are always positive definite. So what that means is that the diagonal entries are very much positive. In fact, most of the weight is in the diagonal entry. So in most applications that we've seen so far in computational algebraic geometry, typically we have matrices with a lot of action on the diagonal. And in physics, it's the opposite. So in this Lorentzian context for massless particles, the diagonal is 0. And this leads to some interesting new phenomena. Okay, now the principal minors, by our inequalities, 4x4 minors are negative. So let's work this out. So I take my matrix, I look at the 4x4 submatrix with row indices I, J, K, and L, and column indices the same. The diagonal entries are 0. So I get this quartic polynomial in 6 unknowns, and that's non-positive, less or equal to 0. Okay, now, but let's do the following thing. Let's formally introduce the square roots. This is an irreducible polynomial, but I'm now going to introduce formally the square root of Sij. I'm going to call it Pij, suggestively for Plücker coordinates. And after the substitution, my quartic factors as a product of 4 quadratic factors. They all look alike, and they're all what's known in math as the Plücker relation. You can see in the factorization, amazingly, we see the Plücker relation, and these 3 brown factors, black factors, are sign adjusted Plücker relation. So in math, we call this the Plücker relation. For the Grassmannian, physicists call this the Schouten identity. And well, and in fact, it's a squaring operation. What this says is that here, if this were 0, we would be in the squared Grassmannian. And that has been studied recently in algebraic statistics, for example, in a recent paper by Friedman. But also, this now guides us to matroids. Why is that? Well, matroids are a combinatorial version of the Grassmannian, and this factorization has revealed the Grassmannian to us. So let's see what we can do with these matroids. So in this talk, in the remaining 39-40 minutes, every matroid has rank 2. So if you know about matroids, this will be a very special case of what you know. If you don't know about matroids, fear not, because I'm going to give you a definition. But this is only rank 2. For the purpose of this talk, by a matroid, I will mean a partition P, a set partition P, of a subset of the first positive integers. So bracket n is shorthand for the first n positive integers. So I pick a subset, and then I partition this subset in any way I want, and I call this partition P. So such a thing is a matroid. And as I said, you can take this for the purpose of this talk as the definition of matroid. Now then, the bases of the matroid are pairs U and V, so particles U and V, that are in distinct parts. So if U is in the ith part and V is in the jth part, and they're distinct, I'm going to call U, V a basis. Now the elements that are not in my subset at all, I'm going to call loops. So a loop of my matroid is an element that's not chosen at all. So in particular with this notation and for the rest of this talk, the number of parts is M. And I want this to be non-trivial. I want there to be at least one basis. So M, the number of parts, should be at least 2. I'm going to write little l for the number of loops. Okay, so I have n particles. I have my matroid, and there are m parts in the partition and l loops. Now, the finest partition, one special case we could take is if I take my subset to be the whole set, and I partition this into singleton. So the ith part is just a singleton I, so this is called the uniform matroid UN. So in this case, m, the number of parts, would be n, the number of particles, and l would be 0. I'm going to define a signed matroid to be a pair P of a matroid in the sense together with a sign vector, but I'm only giving a sign to every non-loop. So I take a sign vector that's indexed by the non-loops, and so this pair of a matroid together with the sign vector, I'm going to call a signed matroid. If you ever heard about oriented matroids, forget everything you heard. These are very different from oriented. These are signed matroids. Now, fixing a signed matroid, I'm now going to define a subset of the massless Mandelstam region. So the massless Mandelstam region, recap, is n by n symmetric matrices of rank exactly R with zeros on the diagonal, massless. And I'm now going to define the stratum indexed by a signed matroid by saying, well, the entry in position ij should be non-zero if ij is a basis and its sign is the product sigma I, sigma j. And if ij is not a basis, then it's 0. So the zeros in the matrix are the non-bases of my matroid, and that is a matroid, satisfies all the requirements precisely because of this surprise appearance of the Plö correlation. So here's the first theorem in the talk. So the massless Mandelstam region has a partition, so I'm fixing n, the number of particles, and R, the rank of my matrices. Then my massless Mandelstam region, again, these are n by n symmetric matrices with zeros on the diagonal and rank exactly R. And this has a disjoint partition over all signed matroids, P sigma. And I'm going to call this part the stratum. And this stratum is non-empty if and only if a certain combinatorial condition holds. And the condition is that the rank is between 3 and m. M is the number of parts in the partition. Or another special case if R of m is equal to 2. So if this holds, then the stratum is non-empty. And in this case, there's a formula for the dimension of the stratum. So this is a semi-algebraic set of this dimension, m times r minus 2 plus n minus l minus r choose 2. And the parameters, again, n is the number of particles, r is the rank of the matrix, one more, r is the rank of the matrix, so this is the space-time dimension, m is the the number of parts in the partition, and then L is the number of loops. So in Veronica's picture, M is the number of distinct directions that you have on the light cone, and L is the number of particles that sit at the origin, that are stuck at the origin. Very good. This is our first theorem. Now, equipped with this theorem, we can turn this around. We can count strata. So let's do a little bit of combinatorics of strata, and then we'll do a little bit of topology on strata. But please interrupt me if there are questions. So we're 26 minutes in, 34 to go. And you can see from the page count, we're doing very well. So if anybody has a question, please interrupt. Okay, so let's do a little counting. So let me look at the Stirling numbers of the second kind. So this is a combinatorial number. So in our context, I call this curly parenthesis n minus 2 over m. And this is the number of partitions of the set n minus L, that's the set I'm partitioning in, into exactly m parts. This counts set partitions of a fixed set into a fixed number of parts. So with that, I have the following corollary. The number of kinematic strata of a fixed dimension is given by some formula. And there are two versions. There's one version for a fixed sign vector. So I tell you in which side of Veronica's cone you lie. For example, if you like Junie He, you're only on the positive side. That's for fixed sigma. Or the union over all. So for fixed sigma, I have this sum, m from R to capital M. That's some upper bound that you can compute. And then for all possible sign vectors, you multiply the term by a power of 2, because you can adjust the signs. For example, here's a table for n equals 4. So I'm fixing n. This is for 4 particles. I'm fixing the rank. The rank of this 4 by 4 matrix can be 2, 3, or 4. And so in top rank 4, there's one full dimensional stratum, and there are 8 up to sign. That's 2 to the n minus 1. But for example, if you say the rank is 2, then on a fixed cell, there are 7, the stratification has 7 three-dimensional strata, 12 two-dimensional strata, and 6 edges, one-dimensional strata. Here's the corresponding table for n equals 5. So let's look at this in a bit more detail. Of course, the strata and any stratification form a poset. Let me describe this combinatorially first. So I'm going to say a matroid P is less or equal to another matroid P prime if every loop of P prime is a loop of P, and the partition P prime refines the partition P. It's a natural way of turning these matroids into a poset. For those of you who know about matroids, this is the same as containment of matroid polytopes. So for P, there's a corresponding polytope, and P prime, there's a corresponding polytope, and if one is contained in the other, then this one is. So let's look at n equals 4, r equals 2. So on a given sign vector, there are 11 strata. So this is this second column here, right? So the second column, you see 4, 6, 1. So this has 4 three-dimensional strata, 6 four-dimensional strata, and 1 five-dimensional strata. And as a cartoon, this can be described by this 2 or 3-dimensional picture. So I'm going to describe this picture. So first of all, this top stratum, so this number 1 here, the top stratum, is actually disconnected. It has 3 connected components. And then there are 6 lower dimensional strata and 4 even lower dimensional strata. And you can visualize this by the faces, the edges and vertices of a tetrahedron. So as a cartoon, think about the 6 edges of a tetrahedron. and think about the 4 vertices of the tetrahedron, except these vertices are now 3-dimensional pieces. But then this is 3 green surfaces that you glue into the tetrahedron. So try to hold the tetrahedron in your hand. So make a tetrahedron out of your fingers. Then out of the 6 edges in your tetrahedron, you can form 3 4 cycles. Okay, so if you not following, you can come back in. Right? So now think about a tetrahedron. It has 6 edges, and there are 3 4 cycles in this graph. And inside this 4 cycle, you glue in a green surface. You take this 4 cycle, you dip it into soap, you pull it out of the soap, and you get a green soapy surface. You do this 3 times, and then the union of these 3 soapy green surfaces is 1 stratum, namely the top stratum. So this is what happens on a fixed sign vector, but of course we also vary the sign vectors. So let's extend our poset structure to the signed matroid. So I'm going to say a signed matroid P sigma is less or equal to another signed matroid P prime sigma prime. Well, if I have the inclusion on the matroids and sigma and sigma prime agree on all non-loops of the smaller. Again, this is a natural way. So you think about these things as a natural way of forming a poset. So let's move a little bit towards the topology. I know that topology is a popular topic, especially in Mexico City. Greetings to everybody in the room. So let's talk a little bit about the topology of the stratification. Well, first of all, the stratification is nice in the sense that if a stratum intersects the closure of another stratum, then the smaller one is contained in the closure of the other. That's what you want, right? You want to have a sort of a proper stratification. Once somebody intersects the closure of somebody else, then it's actually contained. However, the topology of the strata is quite interesting. So I claim that the M0 P sigma 3, let's unravel this again. So I'm looking at n by n symmetric matrices with zeros on the diagonal. I'm fixing the sign pattern of the entries, and I require that this matrix has rank exactly 3. If that is so, then the m minus 1 factorial over 2 connected components. So if m is equal to 3, then these are the 3 connected components, these 3 soapy green soap bubbles, where m is 4. And in general, m is the number of parts in the partition of the matroid. This is the number of connected components. So in combinatorics, this is the number of cyclic permutations, cyclic arrangements of an m element set. So m people go to a Chinese restaurant, they sit around a round table, and this is the number of ways that these people can sit. So if 4 people go to a restaurant, they can sit in 3 different ways. If they can sit in 12 different ways, and so on. Now, here's a theorem. So this kinematic stratum, if I go up to rank R, so if I fix the rank and I take the union up to R, is homotopy equivalent to a well-studied configuration space. So I'm taking the configuration space of m labeled points on the R minus 2 dimensional sphere. If R is 3, then this is the 1-dimensional sphere, and this 1-dimensional sphere is the boundary of the table in the Chinese restaurant. Right? So if I have m points on the 1 sphere, well, there's disconnected ways, one for each way of doing this. But of course, I have to take the rotation by the relevant group, so I have to mod this out by the group of rotations. So this is the configuration space. So this is disconnected if R is 3. If R is 4, something very interesting happens. So then we're talking about a configuration of m labeled points on the two-dimensional sphere. This is the configuration space. And a good way to think about this is to think about the sphere as the Riemann sphere. The Riemann sphere is also the complex projective line, and then the stratum is homotopy equivalent to the moduli space, M0M, and therefore to the complement of the affine Braidericht. Here's one reference from 25 years ago by Ziegler and Eva Feichtner on the integral cohomology of these ordered configuration space or spheres. So there's a fairly substantial literature, and this comes up here when we study the topology of individual pieces. So again, we have this stratification. We know how many strata there are. The stratification is nice in the sense that we have a proper inclusions of closures. However, each piece is not a ball at all. It can be disconnected and can have very interesting homology groups. Very good. So now we are at slide 14 out of 21. So we're doing very, very well. And again, maybe I'll pause for a question. So what have we done so far? Well, we've done so far, we said, let's look at Veronica and her cone. And we have n vectors that are on the boundary somewhere on this paper. Right? And I'm organizing this, I stratify this according to whether these are in the future or in the past or at the cone point. And I work, of course, modulo the relevant symmetry group. And I've described to you the stratification, the algebra, the combinatorics, and a little bit the topology by relating it to configuration spaces. And I hope I was right that configuration spaces of interest in Mexico City.
Yes, I have a question.
Yes, please.
Yes, it's something which is bothering me since the beginning of the conference. And maybe I am trying to imagine something which is not there. Which are the consequences of this result, especially the classification of the strata, if we're trying to look for new invariants in the physical point of view?
Okay, well, I don't know. So are you a physicist? so what?
No, I'm coming from analysis.
let me try to. Okay, then let me
yes,
give.
Yes, I am trying to imagine that is what it really means in this structure.
Okay. So let me try to give an answer. So what?
Okay.
The little I know about physics is about doing integrals. Basically,
okay.
All of physics, one way or another, is about understanding, evaluating integrals somehow, right?
Okay, yeah.
And
I'm coming from analysis, so I share that point of view.
So here, these spaces, these SIJs, these are the kinematic parameters. So in the integral, you have an integrand.
Okay.
The integrand depends on two things. It depends on parameters, and it depends on the stuff that you integrate out.
Okay.
And these are the parameters that are left out after the integration. So this topology gives you information about the integral, about where to integrate, where the possible singularities are. So it's basically a tool so the reason people are interested in this and hopefully find this interesting is because it helps to evaluate integrals. So in particle physics, they would be called scattering amplitudes. In cosmology, they're so-called cosmological correlators. And this kind of geometric stratification gives you information about the integrals and especially about the singularities of these integrals. I don't know whether that's a good answer, but that was the motivation of the co-author who comes from physics.
Oh, yes, I see. So that is something similar to try to evaluate all the elliptic integrals over the complex planes, but it can be applied for higher dimensions.
Absolutely, yeah. So elliptic is a very special case. So elliptic integrals and more general abelian integrals are special case. Now, one approximation to scattering amplitudes are Feynman integrals. So you break up this integral into many, many, many pieces, one over each graph, but each piece will be a function of my Sij. So whenever you do a Feynman integral, what you get at the end will be an expression that depends on Sij.
Okay, yes, I see now. Well, with the Feynman integrals in analysis, it's a little more complicated because we have to consider all the possible distributions rather than continuous trajectories.
Yeah, okay.
Yeah, but
Let me
I
switch it
see the
under the
relationship. Okay.
Yeah.
I,
Do we go
of
on?
course,
Well, let's continue because I am
Please.
going in a very different direction.
yeah, of
Please.
course, these integrals are very complicated in physics. They often diverge, and it's a whole game. I mean, but for simplicity, in the end, what I'm doing here is provide combinatorial tools for the study of integrals that are of interest in physics.
Okay.
Now, what do
Let's continue.
physicists actually want? Okay, now this is my version of your question. What matters for physics? What we're going to do now, we're going to go back to 1958. Mandelstam was actually a person, right? Stanley Mandelstam, and he wrote one very famous paper that has this title in Physical Review in 1958. And the picture on the right is from his paper, Kinematics of the Reactions. So interestingly, in those days, they called them reactions. So, that scattering experiments you do in CERN and elsewhere, so you have some particles come in from the past, they collide, and they make new particles in the future, and it costs the taxpayers a lot of money to do this. And so let me now describe the situation, the special case that's of most interest in physics. And that's the situation when we also have momentum conservation. So this is the case that physicists really care about. So now I'm going to define the MMC region, or massless momentum conserving region, C0NR. And this is obtained by intersecting the Mandelstam region with matrices that have all row sums 0 and all column sums 0. So this is my space of n by n symmetric matrices where now the diagonal entries are 0 and the row sums are 0, and therefore the column sums are also 0. And C0 P sigma R is the intersection of my previous stratum with that subspace. So this is the semi-algebraic set that people really care about most, right? So now Veronica is holding the cone. She has n vectors sprinkled over the paper that makes the boundary, but these n vectors sum up to the 0 vector. That's what you have in an axial scattering experiment. Now that is so, we have the following theorem. We have a theorem that characterizes when this intersected stratum is non-empty. And you can imagine we have to have some particles in the past and some particles in the future. Otherwise, they can't add up to 0. So there's an if and only if condition, but it's a little bit more complicated now. So if and only if two things hold, there's a first condition that says, 3 is between R and M, and there exist particles I, J, K, L, such that I and J are in the future, K and L are in the past, and there's a matroid condition. The restriction of the matroid to this 4-element subset is either uniform or some other matroid. And if R is equal to M, then each part has elements with opposite signs. So this is a combinatorial condition when the stratum is non-empty. Now, in this case, again, there's a dimension formula, and this depends, as before, on n, the number of particles, r, the rank, which is the space-time dimension, m is the number of different directions, the number of parts in the matroid, and L is the number of loops. That's the number of particles that went degenerate, that went to the origin. Now, with 15 minutes left, let me not talk about combinatorics and topology of this now. It gets even more complicated. Let's do one example. And let's do the example where the rank is 3 and the number of particles is 4. Let's try to understand this space when n is 4. Now, if n is 4, this is the plane, right? So this is r squared if n is equal to 4. So now we have an ambient subspace that's a plane, and I wrote for you a general 4x4 symmetric matrix with zeros on the diagonal and all row sums 0. And there are two free parameters, x and y, And now I'm drawing pictures in the XY plane. That's my kinematic space. Now, this is supposed to satisfy our Mandelstam invariant inequalities. So in particular, for example, the 3×3 minors should be non-negative. Now the 4×4, the determinant itself is 0, right? The row sums and column sums are 0. So 1, 1, 1, 1 is in the kernel. But the 3×3 minors, they're all the same. And you can check every 3×3 minor is minus 2 times x times y times x minus y, and that's supposed to be non-negative. So let's draw that region in the plane. Well, there are 3 lines, right? There's the x-axis, the y-axis, and then in diagonal blue, you have where x plus y is 0. And the Mandelstam region is shaded in pink. So this has 9 strata. So the open pink region is where this matrix has rank 3. And on the blue rays, on the 6 blue rays, the rank drops to 2. And then there's the origin where everything is 0. That's disallowed, right? So I have 3 full dimensional strata and 6 lower dimensional strata. Now here, in these curly parentheses, you have the signed matroid. Right? So for example, here, this is the uniform matroid, and then 1 and 4 are in the future, and 2 and 3 are in the past. Okay, so this is the massless momentum conserving region, is this union of the open pink cones and the 6 blue half rays. Now, let's go from massless to massive. So now we no longer, have just photons, but we have protons, bosons, you name it. And let's say these 4 particles have 2 distinct masses. So the first 2 have mass mu, and that's small and positive. And particle 3 and 4 have a positive mass. That's bigger, m. Well, then my matrix gets modified a little bit, right? On the diagonal, in fact, you have these masses squared. You have mu squared on this part and m squared. And again, the row and column sums are 0. And now let's draw the picture. There are 3 versions. On the left, you have when everything is massless. So there we have these 3 polyhedral cones. Now, if we go from massless to massive, but all 4 particles have the same mass, then these cones stay polyhedral cones, but they get pulled apart. Now really they get ripped apart. And now, if in this situation where m is strictly bigger than mu, the linear boundaries become non-linear. So on the right-hand side in picture C, we have 2 unequal masses. So now this is our kinematic region, but now the boundaries are non-linear. And this picture equals the picture from 1958. Now, of course, mathematics is very old, right? So Eduardo just asked about elliptic integrals. Elliptic integrals were introduced by Abel, when Abel traveled to Saxony in 1740. He looked at elliptic integrals, now more generally abelian integrals. So math is very old. It goes to 7, but physics is a bit more recent. So going back to 1958 is ancient. But what I just explained is precisely the picture that Mandelstam gave. So picture is here. You rotate my pink picture by 90 degrees. Then you get these striped regions here. And he calls them the 3 different reactions, 1, 2, and 3, corresponding to my 3 red-pink signed matroids. So this was very gratifying. So not only are many things in this field named after Mandelstam, but we can reproduce using this semi-algebraic geometry, the 2-dimensional picture he had in 1958. Of course, we went further, right? So we also analyzed the case for 5 particles. So for 5 particles, if n is 5, This kinematic space has dimension 6. So now we're looking at 5 by 5 symmetric matrices, zeros on the diagonal, row and column sums 0. So that's a 6-dimensional space with coordinates A, B, C, D, E. Now there are 10 full-dimensional regions. So the maximal rank this can have is 4, and there are 10 regions. These are 4-dimensional regions. If I disregard the sign of the 4 by 4 minors for now, if I focus on the 3 by 3 minors, they are linear. Remember what was Sij times Sik times Sjk. And those linear boundaries define a 4-dimensional polyhedral cone with 10 facets. And that's a cone, I'm sorry, it's a cone in 5 space. So it's a cone over a 4-dimensional polytope. It's a so-called cyclic polytope. So polytope with 6 vertices and 9 facets. That polytope is dual to the polytope we had on my opening slide 51 minutes ago. So this polytope is dual to the direct product of 2 triangles. So the direct product of 2 triangles is a 4-dimensional polytope with 9 vertices, 18 edges, 15 2-dimensional faces, and 6 Toblerones, triangular prism. So the dual polytope is the 4-dimensional Swiss chocolate. But now we're going to work in the 4 by 4 determinant. So the 4 by 4 determinant gives us one additional inequality, and that's saying that the 4 by 4 principal minors are negative, and that's an irreducible blue polynomial, a very famous polynomial in algebraic geometry and number theory. It's called the Igusa quartic. So inside this 5-dimensional cone over the cyclic polytope, I'm carving out a fairly big piece by this inequality, and it's the union of these 10 5-dimensional regions, conical regions, and all their boundaries, and with the full stratification. So that would be Mandelstam's picture in dimension 6. Very good. So this is the end of the talk, and nobody ever minds if a talk ends early. So let me come to the conclusion. So we are part of a so-called ERC synergy project. This is where a bunch of senior people get together and try to create some synergy. So our project is called Positive Geometry, and the middle picture is a cartoon for positive geometry. In particle physics, the left picture is a cartoon for a scattering process. And cosmology, the right picture is a cartoon for the 3-point function. So when you study distributions of galaxies by gravitational waves, and you make these kind of 3-point measurements. And positive geometry is an emerging field at this interface. It's concerned with real, complex, and tropical geometry. And in particular, it studies shapes, real algebraic shapes, semi-algebraic shapes that we discussed today. Now, this talk discussed the collaboration between 2 of the 4 nodes, the Leipzig node and the Princeton node. The cosmology node is in Amsterdam, and then another physics node, the lead node, is in Munich. The particular project I described here was really about combinatorial geometry, and we in fact submitted our paper to this journal called Discrete and Computational Geometry. But there are tons and tons of interesting open problems, and here again is the light cone as we built it, and I thank you for listening.
Thank you. So, do we have any questions for Bernd?
Can I ask a couple questions?
Please.
Oh, okay. So they're mainly on 2 different things. The first is, I think at some point you mentioned this whole set of like matrix polytope inclusions about M0 P sigma R. I don't know if this is a well-defined question, but like, do you have any idea like what kinds of posets you get from like these spaces? Like, yes, you get a poset, but what kind of characteristics do they have?
I don't know. I haven't studied
Okay.
this. That's a very good question. So I think this, containment of matroid polytopes is fairly natural. But
Definitely.
as far as I know, this has not been studied. I think the first time where this gets studied very systematically is this paper that we're all looking forward to, right? So I
Okay.
think you and many other people are looking forward to the latest Juni Matt Baker paper, and where they do this in arbitrary rank. So we're just describing this in rank 2, but these are very interesting spaces. And I think it'd be interesting to study the posets. I don't know.
Cool. So my second kind of question is I forgot which slide it was, but you discussed the topology of these individual strata and this closure type thingy involving the configuration spaces at some point.
Yeah,
Sorry.
Okay, coming up.
Yeah, so I guess when people look at topology and moduli spaces, they often look at, I don't know, signs of order characteristics, some kind of stabilization stuff. Do you have anything along those lines?
Yeah, so stabilization holes, as I said, there's a literature on this. This is an early paper. So yeah, so stabilization holes, if you have n points on a 6-sphere and n goes to infinity, the cohomology will have some stable behavior.
Yes.
So in principle, yes, all of this can be applied. Right? So we have this now, what we have this poset. That's interesting. And so there's poset topology, but then each piece in itself has interesting topology. So I think
Do you know anything with the signs of order characteristic?
Pardon me?
Order characteristic signs.
We didn't compute it.
Oh, okay. That's it. Thank you.
Go for it.
That's fun. Thank you. That's it.
Someone had a question about literature references to read.
Yeah, so I would say our paper is a good place to start, and we're citing, many things. But I think it should be fairly self-contained. I mean, really, I would say if somebody wants to study these kind of, there's also a variety. So here we focus on inequalities. There's also an emerging literature on kinematic varieties, where we always say is, let's fix a symmetric matrix. Let's say the diagonal entries or maybe some diagonal blocks are 0, and we're imposing rank constraints. Okay. So there are some other recent papers where this is studied. So interestingly, these are not generally irreducible varieties. So there's a vast literature on determinantal ideals, but here they are sort of new. And again, partly the reason they're new is with the diagonals being 0 is sort of a new idea. It's very elementary. But if you look at the commutative algebra literature from Genova and elsewhere, these kinematic varieties have not been studied a lot. So there are a couple of recent papers, but there are not many papers that deal with situations where the diagonal entries are 0 and row sums are 0 and so on. It's a situation that's fairly new. Maybe by way of advertisement, so in February and March, next spring, there will be a special program at the Schrödinger Institute in Vienna on amplitudes and algebraic geometry. And the first week, there will be a opening intro lectures, and I'll give a sequence of lectures on kinematic varieties. So this is an emerging topic.
When is that then? Sorry?
February and March 2026.
Okay.
Called Amplitudes. One of the organizers, Lara Bossinger, well known in Mexican math circles, so she very much got into this, perhaps a bit more from a cluster algebra point of view. But kinematic varieties and these kind of semi-algebraic subsets is an interesting emerging field, I would say, as part of positive geometry.
Good. Do we have any more questions for Bernd?
Well, just a small commentary. Thanks a lot for the view of this scattering of the muon pion. Now I understand really what you are doing. Thank you.
Okay, thank you very much. Thank you for your questions and comments.
Yeah.
So before we leave, thank you very much for being here. Thank you very much to Bernd. We will have a second webinar. We'll have 4 webinars this year. The next one is an analysis with some geometry, I think, by Julio Rossi. It's going to happen on the 2nd of July, and the title is The Flow by Minimal Curvature and the Convex Fall of a Set. Probably you might not be interested, but please disseminate this information to your colleagues. We will also try to make this available as much as we can. And something I didn't mention, this webinar series, as I am one of the organizers, but also Carolina Araújo, Maya Stein, who had to leave a moment ago. She's from Mexico, from Chile, sorry, from Santiago Universidad de Chile. And she said that she liked your lecture bank. And the fourth one is Luis Silvestre. He's a professor at the University of Chicago. Okay, so I think we are done. We thank you very much again. See you.
Great.
Thank you, everybody.